Hi, thank you all for coming today. That is a beautiful picture of me doing some mineral separation work with nitrogen, so that was a lot of fun. First of all, I want to thank my awesome mentors, Becky Flowers, Colin Sturrock. Y'all were amazing and really got me through this. And for NSF and UNAVCO, without NSF funding, this wouldn't be possible. And without UNAVCO, I wouldn't be here. So get started. So Craton systems exist worldwide. We are currently on the North American Craton, and these are the stable crustal interior continents. They're typically thought to be relatively unchanged since their amalgamation or since they came together. So these are the basements of the Cratons worldwide. The red that you see, that is Archean in age, and they came together around 4 to 2.5 billion years ago. The blue that you see is Proterozoic in age, and those came together about 2.5 billion years ago to 560 million years ago. And the green you see is Phanerozoic basement, which was after 560 million years ago. So why is this important? Because my study was in the Canadian Shield, and in the Canadian Shield is part of the Craton, and my study specifically was in the Trans-Hudson Orogen. So what was the erosional and burial history of the Trans-Hudson Orogen during the Phanerozoic? That is what I focused on for this summer. And so why does this matter? So overall, in the broader study, this matters because typically, since Cratons have been thought to be unchanged since they came together, we were looking at forces that could be tectonic forces possibly outside the ones that have been typically thought of before. So thermochronology is going to help us with that. So Colin took samples from the Trans-Hudson Orogen Proterozoic basement. We processed these apatite grains, and these will help to rebuild the thermal history of the Trans-Hudson Orogen. The samples that you see to your top left in the bigger picture, those are samples taken by Dr. Flowers, and then the ones in the bottom right under the Superior Province label, those are Colin Sturrock's current study that he's doing. We use the stratigraphy surrounding the Trans-Hudson Orogen because that's going to give us a general idea of what was going on at that time, since the Trans-Hudson Orogen's erosional burial history does not exist anymore. The history surrounding the stratigraphic history is going to help us give an idea of the Trans-Hudson Orogen's history. So we use the Athabasca Basin, which is next to the Trans-Hudson Orogen to the west, the Western Canadian Sedimentary Basin, which is a little further west than the Athabasca Basin, and the Hudson Bay Basin, which is to the east of the Trans-Hudson. So a little background on uranium, thorium, helium thermochronology. So it starts out as the parent, uranium, thorium is our parent, and as it decays into lead, it releases helium, a daughter product. And so to get an apatite helium date, we see how much helium is left in the apatite crystal versus how much uranium thorium content there is in the crystal. Now, thermochronology is a little interesting because apatite crystals are very sensitive to temperature. So the higher the temperature of the crystal, the more that helium will be diffused out of the crystal, and the lower the temperature, the more helium is enclosed or retained in the temperature. We also have a term called closure temperature, which this is the point at which apatites start retaining helium and not diffuse helium anymore. Apatites are very sensitive to temperature change, and because of that, we can start to rebuild an erosional and burial history, because as the basement is eroded, it becomes more exposed, and so the rocks cool, and so then the apatite grains in the rocks start to retain more helium. As it is buried, as the basement is buried, it starts to heat up, and at that point, it starts to diffuse more helium. We also have another factor added into our ages, and that is called the EU value. The EU value is the uranium and thorium content. And so the EU value is, the EU is a proxy for the radiation damage radiation damage will affect the closure temperature of the apatite crystal, or whenever it stops to diffuse helium. The higher the EU value, which is our proxy for radiation damage, or basically the uranium thorium content in the crystal, you will get a higher closure temperature of the apatite grain. So previous thermochronology studies are very important because it's given us an overview of the Canadian Shield. And so my study is fitting into pretty much the middle of these two studies by Flowers and three studies, Flowers and Altell and Sturrock as well. His is apatite dates in the Trans-Hudson Orogen we have found to be some of the oldest in the Canadian Shield that has been found so far. So that was a really, really cool study that came, a really cool result that came out of this study. So the samples were taken. I drew a transect along the samples because I wanted to relate the samples, their dates in time, but also in space along the Trans-Hudson Orogen. This was a transect, and it gave us some really interesting results when we drew this one. Let's not. And I'm sorry, but there's also one in the Western Superior Province in the middle bottom of your screen. And that one is important as well. So, are you ready for the results? The results, we found that these dates from these apatite grains were significantly younger than the Proterozoic basement, which was around, it came together approximately 1.9 to 1.7 billion years ago. Another interesting result that we found is that these apatite helium dates were also as older than the stratigraphic units in the surrounding basin. So the figures that you see on your screen, this is the correlation along space, along the Trans-Hudson Orogen. And so all those little dots with the differing colors, those are the EU values of each apatite grain in each sample. And so what we did was, we have a mean average of the sample, but we also have a date for the sample for each grain in the sample as well. And so that gives us an idea of what was going on during that time whenever it was either buried or eroded. So we're going to start with the youngest date of the Trans-Hudson Orogen transect. And this was, he had a correlation of low EU and relatively younger dates. These three samples, we correlated these together because they were giving off a really good, your top figure is giving off a really good representation of the sample that has been partially reset. It has a low EU with a low helium date age, the triangles on the figure, and then also high EU and high age. Also with that sample, we had one that was consistently a low EU or low radiation damage with somewhat mid-range dates that we were seeing. The figure on the bottom of your screen, this gave us older dates with a limited range of EU, but still relatively low to high EU. These samples were actually these had a really good correlation between they were consistently young dates, they're consistently the same age across the span of EU. So as you went across, as the radiation damage increased, they stayed around this relatively the same age. So that was a really interesting result. The general trend was a younging to the east, except for that very first sample that we went over, the most western sample. That was actually the youngest of the transect, but other than that, we had a general younging trend. So, as I said earlier, the Trans-Hudson Orogen dates, these apatite helium dates are among the oldest in the Canadian Shield that have been studied so far. And this implies that they cooled likely via erosion earlier than other parts of the Shield. The southwestern samples exhibited younger apatite helium dates, especially the youngest one we had was to the southwest. And this may be because it was later exhumation or later reheating, because apatite helium is very sensitive to even a few kilometers of reburial reheating. So our data EU patterns exhibited a greater dispersion than in the northeast. Our northeastern samples exhibited very reproducible, or consistent dates at a higher age in the younger EU, from low to high EU. This indicated possible earlier cooling, likely via erosion. So the flat data EU profile of the northeastern samples suggests possible rapid cooling of the Trans-Hudson Orogen's Proterozoic basement in the northeast due to 447 million years ago to 424 million. Due to the apatite helium dates alone, there may have been possible exhumation from as early as the Cambrian to as late as the Mississippian. The younger dates at lower EU in the southwestern samples suggest either partial resetting or slow cooling due to slower rates of exhumation than the samples in the northeast. The northeast samples cooled earlier or were more rapidly exhumed than the samples to the southwest. And the apatite dates in the Slave Craton and the Western Superior Province are significantly younger than the apatite helium dates in the Trans-Hudson Orogen. So basically, on the edges in the Slave Craton and the Western Superior Province, younger dates, and older dates in the middle in the Trans-Hudson Orogen. This could possibly imply that other forces outside of tectonic forces could be playing a part in intra-Craton instability. And as I said before, I would like to thank NSF, Colorado University, UNAVCO, and my mentors for this wonderful experience and opportunity. Any questions?
All right, questions for Haley? Colin.
Great talk, Haley. I'm very proud. So you mentioned that there's some forces outside of tectonics that might be playing a role here. Can you give an example of what those might be?
So typically with tectonic forces or organic events, the volcanic arcs slamming into a continental crust. But during that time, there was no organic events around 550 million years ago, which was one of our oldest dates that we got. So that in itself is a question, why was that happening? Because during organic events, you get uplift and exhumation, which uplift is the rocks coming up, exhumation is erosion, which is what we're seeing in the middle of the craton. So, to answer your question, it could be a number of things as far as the thing that keeps coming is the mantle convection, possibly in the middle of the craton. So that is a very confusing subject, so I'm not sure how far I want to go into that. So did I answer your question at all?
Yeah. What's the name for that?
What's the date?
No, the name. When you have mantle convection.
Dynamic topography.
There it is.
There it is.
I sense a plant. Any other questions for Haley? It sounds like you guys have talked about it. Any other questions for Haley? No? Oh, sorry.
Yeah, again, great talk. So you mentioned that the basin is Proterozoic.
The basement, yes, it's Proterozoic.
Okay, so and the uplift is younger than and the exhumation is younger than.
Yes, the exhumation is younger because it was eroding the overlying rock on top of the basement, and so we don't have a history of that.
Yeah.
There's no deposition,
So
no rock overlying the basement right now.
yeah, my question is, can you use other methods? Maybe use apatite and the closure temperature is very low. If you use zircon, would you get any better history of the exhumation, for instance? Or are there other studies that use other minerals?
With detrital zircon, I know the detrital zircon studies are more prominent studies, but
Okay.
as far as zircon studies, it's a higher temperature. So I'm not entirely sure if it will give the same results, but it could possibly add more to the story.
Okay.
I'll check into that, but they could possibly add more into the story.
Okay. Yeah. Thank you.
All right. Well, thank you, Haley.